What's up, everybody? Today on Universal Theory, we're going to be doing, as you saw a couple of days ago, we're going to be doing the same thing. We're going to be talking about science and the Hermetic principles. Today is going to be the particle-wave duality, and we're going to be talking about the principle of vibration and correspondence. They pair nicely. We're only using two because we're only doing this in 10 to 15 minutes. But just know all principles always apply to everything inside of our universe. You're not going to get away from that. If you don't understand why that's the case, we did a 8-video series on why that's the case. You can go check that out in the 7 Principles playlist. I will try to remember to link it above in the video. But we're going to be talking about the particle-wave duality, and we touched on that a little bit in the last video. Jordan was alluding to it. I alluded to it. Quantum field theory is kind of based on this idea of the particle-wave duality. So is quantum mechanics. And what we're saying with the particle-wave duality is exactly how it sounds. A particle isn't just a particle in itself. It is a wave and it is a particle in two ways. In quantum mechanics, where that particle is going to be is a probability, as we've talked about. So where it's going to be is a wave. At that point, we can't say that it's a particle. We just know, because if we said, we know it's a particle, Trent, well then where it's going to be wouldn't be probabilistic. If it was a solid particle moving through space, we would know exactly where it was going to be. And so that's the quantum mechanical interpretation, is there's something going on here because we don't know where it's going to be. And then, as I talked about with quantum field theory, well, then we found out that the particle itself vibrates. So we have these two different waves, and they are fundamentally different. Quantum field theory is talking about the wave of the particle itself, and quantum mechanics is talking about the wave of where it's going to be. So the particle-wave duality, you could apply that to either one. And really where it kind of ties back to the metaphysics and the principles is the fact that it is a particle and a wave at the same time, meaning that the substance of it is. That's kind of where I see it. But you could tie both, like I just said. The principles apply to everything. And what's happening when we see a particle is it's just an excitation in the field. It's just energy in the field. And because it's just energy in the field, what's happening is that energy is kind of decohering from the wave itself, right? That's what an electron is. An electron, when we see it, it has decoupled from that wave a bit. So when I say decoupled, it just means that it kind of starts to separate. You could think when you see a particle, the waves in the background, they're not two different things. We need to think about this from a holistic perspective. And when we think about it from a holistic perspective, imagine that when we see the particle, the waves in the background, and they're attached via a rubber band or something. So it's never going to move away from it. That wave is always there in the background. This is something that they found in science, that we can't get away from this. There is the Copenhagen interpretation, which states that every possibility inside of that wave has now collapsed to this particle. But we're to a point now to where we know that's wrong. I mean, it's right enough for the calculations, but when it comes to this kind of conservation, and when it comes to, well, what happens to those other states, and actually, now that we have strong enough computers, when we start to simulate these kind of, okay, I'm going to give you a computational thread that's going to be this probability, this probability, this probability, this probability, a computer doesn't know how to collapse it. So if the world actually acts how we think it acts, then it takes human intervention to say, oh no, it's this one. This is the one it collapses to. A computer's like, no, all these. It exists as all of these. So yeah, it gets pretty profound. And as we mentioned in the last episode, well, why are we bringing science and religion together? We don't do that with any kind of ill will or any kind of naivety. We're not naive about it at all. You don't just willy-nilly do this. You do this with a lot of research and a lot of understanding of both the science and the metaphysics. And I get why, because you can get zealots that don't really understand either, and they're combining concepts, and we see it all the time. That is not what we're doing. We are the opposite of that. So, and you should see that through our work and through our studies and through the content that we bring to you, that we are not willy-nilly tying these two things together. So with that being said, how would you, with this whole particle wave duality, I know you touched on it, but do you want to kind of talk about vibration and correspondence, however kind of you feel fit?
Yes. Well, we talked about, before in the previous video. So if you haven't seen it, then go back and watch it. But in just now, we're talking about the excitations in the wave, and that's what a particle is. And then we talked about resting mass, and we talked about how, well, we didn't get into it, but this resting mass is a given amount of energy that has to happen for a particular type of particle to manifest. So electrons is 0.511
mega electron volts.
Mega electron volts. I always get that wrong.
Make electrons voltage again.
So this is a vibration, and it's a specific type of vibration or a specific frequency pattern that corresponds to an electron in this giving instance.
Yep.
And then you're not going to see this specific particle or an electron manifest any other way but in integers of 0.511 MeV, mega electron volts.
Got it.
So nailed it. So equal in nature, different in degree. Other particles by nature also interact in the field, and they're also excitations in the field, but they have to have specific vibratory patterns, or they don't manifest. And if they do manifest with these specific vibratory patterns, they have to happen in integers of these specific frequency patterns. So once again, they correspond. A specific type of particle corresponds to a specific type of excitation in the wave, and then that excitation happens at specific integers. So, and then that also corresponds to us being vibratory mechanisms and being comprised of these particles making up atoms and molecules and cells and organelles and organs and organ systems and organisms. And we also have a wave function.
Yes, we do. Yeah, which is so small. Yeah.
Yes. So, and it's and like he was saying about being decoupled or decohered from the field to some degree, but not entirely. It's not like this wave pattern, it disappears once we are a particular manifestation of the wave or the field. Once we're manifested as what we call organic matter or inorganic matter, it's not totally decohered from the wave, but there is a bit of decoherence from the wave, which goes into what we talked about. Some of these people talking about this science, and they're using pseudoscience because they're not really understanding how it works, because they're blurring the lines when it comes to physics and metaphysics, and certain metaphysical concepts, they can be perfectly aligned with physics, but only when they correspond properly.
Right.
So we're, talking about, let's say if I turn around and my house is behind me, does my house turn into a wave function?
Right.
And it's not decohered from the field, and it's purely a wave. And it's like, well, someone might say, well, if someone else is watching it out the window, it's still a collapsed version of the wave or the field. And it's like, no, that's not how that works.
No, that's not how it works. Nope, not at all.
So, equal in nature, different in degree. It's not to say that it doesn't have properties. It's not to say that it doesn't have a field to each one of these individual particles and the atoms. A wave.
Oh, sorry. And a field. It's corresponding. Yes. Sorry. Yep.
Yes. So it's not like it doesn't have these properties. It does. It's just that it's been decohered, like he said, to some degree. There's a sufficient amount of energy or a sufficient amount of, correct me if I'm wrong, electrons that are present that allows it to decohere from the field.
Just that there has to be, if you're talking about, there has to be enough interaction events.
Yes.
Or measuring events. And if there's enough measuring events, then that holds that particle in place, because it not measuring as looking at it, that could be one thing, but it could be being measured by another particle. If another particle comes near that particle, now it's measuring it. So it has to interact. It's not like it's going to act like it doesn't exist and fly past it. That kind of causes that decoherence. Yeah.
Yes, exactly. Yeah, I seen a physicist talking about that. And that was a great way of explaining it.
Thanks.
But I was like, okay, I was like, that makes sense, because I was wondering, I'm like, well, if that's the case, does it turn into a wave and you're not observing it, or is the universe itself observing it? And like he said, if another particle comes along, it's like, that's observation. Observation is not just human eyes, and that's a human centric viewpoint.
Yeah.
And we have machines that can observe it. So all it is, if I'm not mistaken, it's these other wave patterns interacting with it.
Yeah, essentially. Yeah, it's just this other energy or whatever you want to call it is interacting with that particle now. So it's bound. It's bound in that decohered state. That's why your house doesn't disappear when you turn around, because there's all those other particles that are interacting with each other that are not allowing for them to be, shot free, and then they're existing by themselves and then being able to, go back into that kind of wave-like probability. But that doesn't change the quantum field theory aspect, as we talked about. That particle is still vibrating.
Yes.
And that's why it's important to remember the distinction between the two. Yeah,
Yes.
It's still always an excitation in the field.
Yeah, it never ceased. So I think that's the problem, is when people find that out, they're like, oh, my house, my dog, it's an excitation in the field. So if he craps on the carpet and I'm not there, did he crap on the carpet?
Right.
It's like, well, when you get home, is there crap on your carpet?
Yeah, exactly. Yeah.
It's not like you turn your head. It's not like you walk in your house, you don't see the crap, but you smell it.
Right.
Did you collapse it because you smelled it, or did you smell it because it collapsed on your carpet?
Yeah, some of that stuff is kind of common sense. You got to remember to use that. A lot of this is anti-intuitive, but that's what we're here for, is to kind of help you get that intuition of these systems. And then, that idea of your dog not existing because nobody can see it will slowly fade into oblivion.
Yeah, which, in closing, the vibration of observation determines the outcome, and that's correspondence. So these vibratory patterns are corresponding with other vibratory patterns, and it's very simple when we say it in that way, but there's a lot of math involved to determine what determines a collapse and how a thing collapses, or to what degree it decoheres from the field. This is the more rigorous scientific training that somebody has to undergo, to truly conceptualize the metaphysical and physical, to put them together into a singular, coherent whole that is scientifically accurate. And it's something that we can use practically, versus just telling someone that, hey, if you turn around, your house doesn't exist.
Exactly. Yeah, one little analogy that I like to use is, when we're thinking about a wave, imagine that it's a car moving down the road, and all that energy associated with that car's motion, right? It's moving. And when you pump the brakes in the car, for some reason you're pumping the brakes, a squirrel comes across, and you pump the brakes because you don't want to hit it. That energy that has now left your car is that electron, right? Except that energy is no longer associated with the car anymore. So that's where the analogy breaks down. But you can see that that's kind of how they're related. That's what happens, is it, you hit the brakes, or some of that energy kind of slows down, and now we have an electron.